to Omar Knio, who is currently a professor and director of uncertainty and risk assessment at Duke Mechanical Engineering and Material Science. So Omar graduated his PhD from MIT in 1990, and his academic career has been in Johns Hopkins from 1991 to 2011 before recruited by Duke. Beyond the academic career, he has an interesting CV here. He's a co-founder and senior vice president of Reactive Nanotechnologies. And among many different awards, here I will cite a couple. One is his Distinguished Alumnus Award from American University of Beirut in 2005, and then he also won a Friedrich Wilhelm Bessel Award given by Humboldt Foundation, as well as R&D 100 Award for nanofoil product from R&D magazine. So the stage is all yours on uncertainty quantification and parametric inference in ocean and general circulation models.
Thank you very much, John. Thanks everybody for coming, and thank you all for the invitation. So I had the privilege of, for the first time in my life, going through an experience of the Applied Math Club this morning, where I spoke about things related to business and politics. Today is this afternoon is another timely subject. I'm going to be talking about ocean circulation models, but specifically focusing on the response of the ocean to hurricanes. And I guess if we looked at the news or out the window lately, we know how important this subject is. This work is in collaboration with students and postdoctoral Q collaborators at MIT. Hamad Sandarani, I don't know how to pitch him. He's actually my friend from kindergarten. It's true. He's the lead PI also in this effort. A quick word of introduction. If you want to read what's on the slide, be my guest. The main takeaway here is ocean general circulation models. Forget the typo here. Are very complicated models. They have a lot of subparts. They have a lot of components, and each of the components involve widgets that we call parametrizations. And just to give you an idea of what a refined model or a refined calculation of the ocean, it has a grid size of about 1 kilometer. And this is really something that is quite refined, at least on a general or a global scale. And clearly it doesn't account for the small-scale oceans, so we really need a lot of representations for all the physics that we are inherently not able to represent on the grid. The way that these parametrizations are constructed involve uncertainties. There are uncertainties in the measurements. There are uncertainties in the models themselves. And what we would like to do is, at least this is part of an effort that looks systematically at assessing what the impact of these uncertainties are, and looking at ways of potentially reducing them or being able to better manage them. The objective here that is driving this work is exploiting large-scale databases, and I'd like to point on this subject a few times as we go along, that let us provide the framework for us to learn how to sample effectively, how to propagate uncertainties effectively, and then using some new experimental measurements that are summarized AXPT. A is for airborne, X is for expendable, the B is for bathymetry, and the T is thermometry. Okay, so these are temperature probes that are shot by airplane, and they go down the ocean, and they give us a vertical temperature profile. And part of the difficulty of the ocean, unlike the atmosphere, is we don't have radar. So the waves go about a few centimeters, and we really cannot look because of density ratios are 1001 with respect to Okay, so a little bit of an outline. I'd like to say, why we want to do uncertainty a little bit more, talk about the ocean circulation database, new approaches for us to be able to sample effectively, and then look at initial work and preliminary work on inference of the coupling parameter, and the focus is going to be on the coupling between the ocean and the atmosphere. Okay, so this is at least my own biased and very twisted view of UQ. Okay, UQ means a whole lot of different things to a whole lot of different people. In a different talk, I may change my mind, but at least for this talk, it's the following simplification. So if you don't have any assumptions, we can't get anywhere. Okay, on this axis, I have data. The data is uncertain. The equations or the model, I know what they are. Okay, once I fix the data, I can read here on this response surface a data point. And on the left axis, I have generally a 3D time-dependent solution. Okay? I call this a probabilistic framework in the sense that the data points in here have weights. Okay, so this realization may be more likely than the realization next to it, and the x-axis is essentially a probability space. And I'm going to be interested in looking, at least in this probability space or in this axis, to introduce representations that are Fourier-like expansion. For reasons that are really not very important, they are known as polynomial chaos expansion. The wording goes back to Wiener. I don't necessarily like it, but I don't have the courage to stand up to Wiener. So just join the club if you don't like it. So once we have fixed the data, we are able to find a solution, and the weight that is associated with the data gets pushed to the solution, and we are able to push probabilities this way through this response surface on the space of solutions. So we're able to say that this solution is more likely than this one if this data point is more likely than the other. Okay? And we are able to work this way. And the stochastic solution, meaning the ensemble of solution and the weights that are associated with them, is solved in a product space, which is a product of a probability space which lives on this x-axis, and the deterministic solution space on the y-axis, and this is how we go. Both are assumed to have a Hilbert space structure, so I'm able to look at them as essentially as xy plane, and I'm able to form inner products and look at coordinates and do the usual machinery of functional analysis and approximation. Okay? This is, polynomial chaos simplified. Okay? I do have some random variables, which I'm going to call C. This C is generally a vector of random parameters. It's really a vector of canonical random variables that parameterize the uncertain parameters. C is time and X is the solution. And the complete, stochastic solution is expanded in terms of modes, which depend on space and time, which I think of, amplitudes or coefficients of a vector. And these functions, ck, are orthogonal functions in these variables in the space, which is the x-axis that I showed on the slide before. It looks like Fourier expansion. It works like Fourier expansion. Think of it as a generalized Fourier expansion. But think of these modes as amplitudes. And this is the basis of the probability space in which the data lives. And we're also assuming, for the sake of simplicity, that the solution is also living in the same product space. Okay? Example of orthogonal functions really depends on the measure of the space. If you use uniform measure on one-to-one, the orthogonal functions are the Legendre polynomial. If you take Gaussian as your canonical random variable, then these are the classical example of the Hermites. This is the only picture of Legendre that I could find, and for the younger generation, don't think that people 700 years ago didn't have ideas of nice hairdos. Anyway, the model I'm interested in, forces me not to follow a Fourier analysis or a Galerkin machinery. It's way too complicated for me to be able to work these expansion into it. And what I'm forced to do is essentially sampling the model. So the approach, of course, the unknown that we are after are the Fourier coefficients. And the way that we are going to find them is essentially like a discrete collocation Fourier method. Okay? So what we're going to have to do is, use a numerical quadrature for quantities of interest, which I'm denoting Q, and then exploit the orthogonality of the basis and run things through a numerical quadrature in order to find the unknown mode coefficients Qk. And once I have the modes in this probability space, then all the moments that I'm interested in, means, variances, higher order moments, simply fall out of the knowledge of these coefficients, much the same way as energies fall out from the knowledge of the Fourier coefficients in a usual expansion. Okay? Why do I want to do this? I'm going to skip over here because I want to show you some interesting pictures. When spectral methods work, they're really hard to beat. This is something that is nice. The probabilistic framework is nice because this is something I'm really attached to because it really provides us fundamental tools for analyzing stochastic error, looking at convergence, looking at distance between distribution, linking into the tools of information theory. So this is something that is really nice. The format of the expansion turns out to be key because it is precisely through that key that I'm able to open the door to all the machinery of approximation theory. Okay? If I just do random sampling, then I have a bunch of random data points, and okay, they're nice, they fall on the surface, I really don't know how they're connected. I'm not able to assess sensitivities that easily. I'm not able to form Jacobian. I'm not able to assess local sensitivities. You want to go to more complicated things like Hessians and go to optimization or inference, it becomes very, very difficult. So the key thing out of this representation that we're after, one of the key aspects is the format, and it opens the door to all of these problems, and we're going to look into this. Okay, this first application I would like to touch on is trying to look at sensitivities on the role of in the parameters that specify the coupling between the winds and the ocean. Okay, what we are solving for is the oceanic circulation. The winds are given to us. Okay, let's assume that they are completely deterministic. But the ocean model, has lots of parameterizations, and we're going to look at the subgrid mixing parameterization as being uncertain, and we're going to look at the drag coefficient also as being uncertain. This is not Sandy, this is Ivan. Ivan was, as capricious as Sandy. It just went and made a loop, which is unusual, so it really wanted to torment Florida twice. And we did have a few data points. They really weren't plentiful. But what we like about the Gulf of Mexico is that on the scale of the global ocean, it's a tiny, nice swimming pool. So we're able to run a lot of calculations that are highly resolved. And the boundary conditions tend to be nice, so the states of the oceanic circulation is relatively well understood. Okay? So, I don't expect you to know a whole lot about these parameters. The subgrid mixing is a parameterization, or if you want to, is a modeling of all the internal motion that the grid cannot resolve. At least with respect to the model that we have, it is the so-called KPP model. It has three parameters, which are a Richardson number, a background viscosity, and a background diffusivity. And the ranges that they come up with are fairly large. The drag coefficient, it has a fairly extensive or elaborate parameterization. But if we just look at it from 30,000 feet, I have a drag coefficient which couples the atmosphere to the ocean, which is a function of the wind velocity. And these are the data points, and the curve that is in pink is really the default curve that goes into the operational forecast that feed into some of the predictions that you see on, updated in the news as far as how much uptake is this hurricane being fed from the hot waters of the Gulf of Mexico or in the Pacific, and what is Sandy going to do over the next 3 to 6 hours, 12 hours, 3 days. Okay? So as you can see, the data is quite spread out, and we would like to understand what the effect of these uncertainties are, at least on relatively short forecasts of the order of 2 to 6 weeks, anywhere of a few days to a few weeks. Okay? Tell you what a prediction looks like. This is the hurricane. It tends to mix the waters. What we're looking at is what the so-called mixed layer depth. This is the top layer of the ocean where the properties are fairly uniform due to the intense mixing. And as the hurricane comes and you can see its track, then the mixed layer depth is increasing because of its stirring motion. It leaves a weight behind it where you know, the mixed layer depth is increasing. The point in here is really not part of the calculation. This is one point where we had a buoy during the path of the hurricane, and we have data, and we would want to do some comparison. The model that we're running is called HICOM. It's fairly resolved. A couple of years ago when we started, this used to be some of the highest resolution. Now we're dropping to 1/50th of a degree, roughly a kilometer cell size. And the time period that we have is September 1 to 10, 2004. T equals 0 just because, you know, engineers always like, you know, T equals 0 sometime, and mathematicians too. We don't like universal times. We switch T equals 0 to midnight, September 1, and this is, you know, some of the numbers or some of the labels that you see on the plots. So we want to sample these parameters. I live in a 4-dimensional space. You know, the typical way of doing high-order sampling is Gauss quadrature. There is a problem with Gauss quadrature is that if you don't like the resolution, you have to toss away all of the points, and then, you know, every time you change the resolution level or the underlying one-dimensional quadrature, you have to throw everything out. In the context of a very expensive ocean circulation model, we're really not in a position to do that. So one thing we are forced to do is to look at nested quadrature. So if I want to go from one resolution level to another, I don't throw the previous calculations. And then, you know, some of the initial ideas that we started experimenting with are the so-called sparse quadrature. And the points in blue are a so-called fully tensorized quadrature. I do the same thing in one direction. And the points in green are the points of a small sparse quadrature. That is, you know, some of these circles are not limited as we go higher in resolution level. This initial attempt at sampling thing is called non-adaptive or isotropic, in the sense that if I don't like my resolution, I refine uniformly in all dimensions of my random parameter space. With respect to my initial picture, the entire space, 4-dimensional space, was shown as the x-axis. Okay? And then we're going to look at adaptive extensions and then suit them and then go to an actual prediction and try to learn something about the data that hopefully one day we will use in order to do inference or better calibration of our ocean parameterizations, or at least the parameters in our ocean parameterizations. How does it work? So I increase the number of resolution levels. So P is the number of resolution level or the order of my expansion. Okay. So, and as I increased, and I'm looking at sea surface temperature at the buoy location, and, you know, by the time I get to a 5th resolution level or to a 5th order expansion, at least in distribution, things appear to be quieting down. So I know that I've sufficiently sampled my parameter space. And at that level, I need about 385 realizations. And even though these are quite expensive, there are two things that, at least on short time scale, A, I can afford to compute them. And the important thing about it is I can afford to store them. Okay? And really a big key of success in what we do is our ability to form massive databases and come back and query these massive databases in order to learn something about better sampling, or in order to learn something about the physics that we're interested in exploring. If you look at, you know, how well we're doing with respect to the buoy that I showed you earlier, this is the observed value, so at least we're really not that far off. I should caution that really one should not compare, you know, a point that is in a 3 kilometer by 3 kilometer grid to one point which is a buoy that is floating in the ocean, because the cell size obviously doesn't have either the spatial scales nor the temporal scales to show the same thing. So the comparison is a little bit qualitative at this end, at this stage, but at least it shows that, you know, the calculation is really not way off. We can look at variance analysis. Question? Yes.
What do you mean by 385 is corresponding to the number of the
coefficients in the polynomial case?
No, these are the number of realizations.
Realizations.
Okay.
But
So if you look at this grid, and remember that I'm showing 2 dimensions. Okay, at level 5, which is roughly here. Okay. So we're able to. This is essentially a level 3 because a level 5 lets us capture exactly a 5th order function. So I have 11 points on this axis. Okay, so this is two refinement level, but you're doing it in 4 dimensions. Okay? So instead of 6 to the power 4 that we really need, we have 385, so a much smaller number of realization than a fully tensorized quadrature. Okay? So the sparse quadrature essentially are an initial attempt at mitigating the so-called curse of dimensionality that you have in order to represent things in high dimensional space. Okay? Some of the metrics that oceanographers do is look at skill metrics. So what they typically do is draw boxes like this box that they have drawn in here, and they compare prediction of different models. And in here you can see the track of the hurricane, and we can look at average temperature in this box. So this is the mean sea surface temperature in the skill region, and we can also look at heat flux in a radius around the center of the hurricane. Okay, so this is the net energy uptake that is that the ocean that leaves the ocean and feeds the hurricane and makes it a more intense weather event. Okay? If I look at the average sea surface temperature, one of the things that was surprising to us is that it shows the same non-Gaussian behavior that the point measurement showed. Okay, this was a little bit surprising because the general rule is that you average things sufficiently enough, then you would expect things to look Gaussian. And in fact, I told my student postdoc, when we know right now go to the skill region and we average the temperature, all of this is going to look Gaussian, and we really are not going to need. But the reason for this is really the drag. Turns out that this is the drag at the high wind speed, and if they're behaving one way in a part of that skill region, they're going to behave the same way at all points. So in retrospect, it is really not surprising that we see these extended tails towards the low temperature, which come from the high wind speeds, in other words, from the high drag of the ocean. And it shows us that even for simple problems like the one that we are looking at, and a relatively low dimensional parameter space that we are trying to characterize, it is really important to go into a machinery that lets us handle the non-Gaussian statistics. So we really needed to go up to 4th, 5th order in order to capture the response of the circulation to these uncertain parameters that we have. Okay? Global sensitivity index, at least we had a whole session about it in the morning. I can see people who did not sleep and they are smiling. So that at least is pretty good. I'm looking at total sensitivity, and forget about this mumbo jumbo of these equations. I have a solution that is expressed in a functional representation like this. And I want to look at the impact of specific parameters. Okay? And since this is an orthogonal function decomposition, the total variance is really the sum of the coefficient times this is the usual Parseval type formulas that we all have seen before. And all I'm doing here is looking at the contribution to the total variance of a certain parameter. I'm coming here and collecting all the polynomials or all that involve that variable. Okay? And I come up with a total sensitivity index. Okay? If I want to look at the total sensitivity on sea surface height, okay, this is something that also has been in the news quite a bit. At least at the time when the hurricane is, you can see that it's just starting to enter, then I see that the first variable, which is the Richardson number, has extremely low sensitivity, meaning it's totally unimportant. Low sensitivity is totally unimportant. Low sensitivity except possibly in here. In all of the Gulf of Mexico, it's totally unimportant. And what dominates sensitivity is really the drag coefficient. So at least we learned from this initial set of experiments that, you know, over the weather events like the passage of the hurricane, it is really the coupling of the atmosphere to the ocean that carries the variance of the solution, or the highest sensitivity, or the highest uncertainty, and we really needed to focus on this much more so than internal dissipation. Okay? Let me skip over this. So we had built this isotropic database, and it told us that, you know, it is really the fourth dimension, or the last variable, that really was most important, at least as far as the variance of the solution is concerned. And the question was, since we had one variable that was dominant, did we really need the same refinement in all directions, or could we get away with refining less in the other directions? Again, we are interested in doing a global sampling of the solution in order to learn the statistics with the cheapest possible way. So I really cannot afford to simply let Monte Carlo loose, or just sample isotropically all directions until things quiet down, right? The nice thing about doing this is that we really wanted to make sure that the driver that we developed was decent before we use it in a situation, and the next situation that we wanted to use it in was an honest-to-God, totally predictive situation, at least as far as the sampling is concerned, in the Pacific. And there, we couldn't afford to run hundreds of realizations and throw them away every few days that we want. So the availability of this database that we computed and stored really turned out to be nice for a priori testing of the quadrature, meaning, okay, here are the realizations. Let me see how adaptive sampling works on something that I've already pre-computed. So the cost is prepaid. Okay? And a priori testing of error indicator. Where do we stop, how much we refine, etc., etc., etc. Now, I want to show you a little bit more about the physics, so I'm going to go a little bit about this. After, you know, we got comfortable with adaptive sampling, we wanted to go and see if we can sample the Pacific in an efficient manner. And in the Pacific, we had, you know, the so-called ITOP experiment. Enough acronyms. I'll show you what ITOP is, and then if you're interested, I'll decompress it. And the question was, can the ITOP experiment, or the vertical temperature structure that it gave us, tell us something about, you know, the distribution of these parameters and how the ocean atmosphere momentum coupling, can it inform us a little bit about it so that we refine these big ranges that we started out. Okay? The adaptive sampling that we have is based on a neat construction. It is called a pseudospectral adaptive construction. And it is based on, you know, taking general refinement grids. These are either orders or refinement levels in different directions, which give us a certain, you know, sparse grid. You know, you're looking either at, you know, refinement levels or multi-indices. This is really not that important. The important thing about it is that if we wanted to treat this as a quadrature, we would run into a problem, because if we truncate at a given order, I really need to fill the entire triangle. Okay? And what the pseudospectral construction does is takes the standard or the classical ideas of Smolyak and breaks this grid or this refinement approach into essentially rectangles which look like projection. Okay? And one of the advantages of doing this, so let me take a grid or a refined grid that looks like this. We break it into a rectangle this way, we break it into a rectangle this way, and you break it into a rectangle this way. Okay? And all of a sudden, by doing this, and these ideas, it's really amazing that, you know, between Smolyak and 2011, they haven't been discovered earlier. By doing this, all issues related to internal aliasing go out of the window. Okay? So we are able to compute all the polynomials that are computable with these realizations without internal aliasing. Okay? And without this decomposition, you really realize that it is hard, because if you want to compute x6, which is y to the power 6, and you have x to the power 6, you have to compute all of these grids that are on the diagonal truncation and below. Okay? Here I'm able to compute a 6th-order polynomial, a 6th-order polynomial, and second-order cross polynomials on this grid. Okay? Obviously, you cannot do it with a single quadrature, so the decomposition has to do that on the fly, and this is what the algorithm does. Okay? Let me skip on how it does it, but the refinement, part of this procedure is every time we add a new grid point, or we refine in a given direction, okay, we compute a surplus of the variance, and then we use a greedy algorithm, and we use that surplus as an error indicator, and the cell that has the highest error indicator gets tagged for future refinement. Okay? Obviously, there are really no guarantees of convergence, and you are always, in the cases of spectral gaps, are able to come up with counterexample. But in general, except in those catastrophic, situations which are really just counterexamples, and you rarely see, greedy algorithms tend to be working very, very well in even very complicated situations. All right. So we had this scheme, and we wanted to see what went on here. And what I'm looking at is how the relative error goes. And I'm looking at sea surface temperature at a given time. Remember, the full database had initially 385 realization. We enriched it in the important direction to 500 realization. And by adaptive sampling, when I measure error or relative error, and we did an honest-to-God job and went to Latin hypercube, so I'm not measuring error on the same grid that I'm using to construct the polynomial representation. With about 60-70 realization, I saturate. Okay? So I'm able to go from 500 to about 60 and 70, at least for this example. And it turns out that if I look at a different time between, essentially you can see what the adaptive is doing and non-adaptive when measuring L2 errors with respect to an independent sample, which is a highly refined Latin hypercube. When we do things adaptively with about on the order of 70-80 realization, we get to the same error level, whereas if we sample isotropically or non-adaptively, with every refinement level we're adding hundreds of additional realizations, as opposed to going strategically in those directions, or designing and computing those data points that give us the most information. And again, most information measured here with respect to those that give us the highest bang as far as the variance of the solution is concerned. Okay, so we're pretty happy with that. If I look at sea surface temperature, and you look at the impact of the fourth dimension, which is the wind drag coefficient, this is how it looks. I'm looking here at all the data. So the variation of the data in all other direction, and the important one tends to be in the third direction, is this much. And in the fourth direction, which is the drag coefficient that I'm plotting here, is between 28 degrees and 26 degrees. Large variation. 2 degrees in the ocean is huge. 2 degrees is the difference between, hurricane and little nothing. Okay? But look where the variation is taking place. It's here. You look at, derivative sensitivities with respect to, to the center of the, and the fourth direction is totally meaningless. You will never sample this way. If we look at the adjoint here, it will tell us nothing. Okay? And in fact, it will tell us that this parameter, the drag, is the least important, whereas in reality it is the most important because it carries all of the variation. All right? Enough, we can do things on composite error indicator. We can look at sea surface temperature and heat flux, and we built going through the algorithmic construction, the mathematics, the source of internal aliasing, the design of the algorithm, the testing, the exploitation of a pre-computed database that let us, ascertain and verify performance before we let the tool loose. We built enough confidence that we are, and we looked at multiple quantities of interest. We built enough confidence in the sampling that we can design a driver and let it go. Okay? And the multiple quantities of interest turned out to be important because it is really not necessary that all refining one quantity of interest will lead you to the same refinement scheme or the same grid as the others. But in this particular case, at least until under hurricane type events, whether you're looking at sea surface temperature, sea surface height, or mixed layer depth, which are really most important from an ocean atmosphere coupling, whether you base the refinement on one quantity, on the other, or all three together, it's really these 60, 70, 80 realizations that carry most of the information. And all the rest have very little contribution to the variance. Okay. Now to the ITOP information, which is something that is more like the news. So this, I am told, is really a piece of luck. The ocean community, I'm part of that community to the extent that I helped them out, convinced the Navy that we needed to buy a whole lot of probes and sprinkle them one at a time. And the probes were funded, they were built, and Mother Nature played tricks on us. And they loaded them on the airplane, and the hurricane season came, and the hurricane season went, and there were no hurricanes. And all of a sudden, Fanapi and Malakas came, and there were all these probes. So the people that built them, decided that they want to go and throw them like crazy because otherwise, all this research funding would go and you build one probe. So lots of courageous people went in airplanes, and these are the paths of the airplanes. So the center of the hurricane is in here, and these crosses or points are where the probes were dropped. And because the hurricane season was kind of empty, a very, very good thing happened, or it was sparse, there were no hurricanes. We got lots of data for one weather event. Okay? This is something that we really can't dream of getting things like this. So even though Mother Nature played tricks on us, it turned out, at least for the modelers, this is a fantastic thing. Okay? A few things about Typhoon Fanapi. I guess with respect to Sandy, it's really not that exciting, but these are a few data points. It really coincided with this ITOP field campaign, and lots of probes were thrown into its path. Okay? This is what AXBT probes give us. So on the x-axis, I have depth. 0 is surface, goes negative, goes down. And what you're looking at on the x-axis is temperature. So it's really warm temperature. You can see the mixed layer up here, and then it drops. Okay. And then you have different place. So this is the flight of one flight, another flight, and we simply plotted all the data on just to show what the temperature profiles look like. And you can see there is quite a bit of variation. If you drop 500 meters, temperature drops quite a bit, right? Wind forcing turns out to be a miserable story. It's really not easy to get wind forcing. And our first attempt at calibrating the wind drag failed miserably. And then we looked at the winds, and we had lousy winds. And from respect of the people who looked at providing us the winds, it was a totally catastrophic thing. Because the model, called WRF, was typically run at 10-kilometer resolution, which is much nicer than the 800 miles that Sandy is operating at. So this was considered to be a highly resolved wind field. But once you looked at the track of the hurricane, the computed versus the observed, they were in different places. So we told them, we wasted a few months of computing, can you go fix the winds? And they fixed them, dropped from 12 kilometers to 4 kilometers. And we said, well, this is really nice, but we wasted another 2 months of computing. When you dropped it from 12 to 4, it made it worse. And then they dropped it from 4 to 1.3 kilometers, which I'm showing in here. And then we could get wind and hurricane tracks that do agree. You know, I'm showing, you know, Fanapi and Malakas, but at least the winds. This involved really a big effort from an entire atmospheric team that really they worked their hearts out in order to give us the right forcing. And if you really don't have an interplay, you know, you can run the exercise, you can run the statistics, and the statistics will tell you it's all model error. You have a systematic bias, closed shop, let's go home, problem done. You can learn nothing from this data, and that's the conclusion. And you really must, you know, being an applied mathematician means, you know, sometimes you have to be under the machine fixing the cryo pump in order to prove your theory right. And this is, you know, yeah, you should smile. And you know, part of running machinery and operation, you know, the theory is, if you know a little bit of math and have a whole lot of courage, there is nothing you can do. And this is for trust me. Anyway, so it was a interactive, painstaking affair in order to get the right forcing conditions, so at least we are able to look at the impact of parameters as opposed to it's all incorrect forcing and this is all the statistics is going to force. Just to show you what, you know, give you an example. This is the 12-kilometer track. Okay, the red is the true. The 4-kilometer did this. Okay, and once we dropped it into a higher level of nesting, could we get hurricane tracks? This is the pink and the red, or the purple and the red, that do agree with each other. Obviously, if you run inference on this or on this, where you think, you know, the code thinks the hurricane is here, the observation know that the hurricane is here, then we're comparing apples to oranges, and this is really systematic bias. This is what the statistics will tell us. Okay? So in order to be able to, you know, learn something, we had to get the right setting, and you know, we had to fix the leak in the cryo pump and yes. Having done the sensitivity assessment in the Gulf of Mexico, we knew that the drag was the most important. We did a more elaborate parametrization of the drag into a 3-parameter family, and we have a multiplicative factor alpha, a saturation wind speed V max, and a slope beyond the saturation speed V max. And let me tell you in a little bit what is going on. So we know the wind drag. So we have an uncertainty alpha, which is we really are not sure where the curve is in here. Okay, this is what the alpha is. We know that the wind drag is going to increase with speed. Why? I have to wake some people up. If I blow harder on the ocean, why would the drag increase? Yes, because we have waves. And then why does it saturate? And some model it says it saturates, and some model it says it drops.
Because waves don't get time to
yes,
increase.
Everybody agrees. So at least I buy this. Everybody is in sync. So if you blow very hard, you won't grow bigger waves, but you will shear the waves. And in fact, there are different theories. One of them says it's going to saturate, so this is m equals 0, and other theories that says no, it's going to drop after saturation, and we have a negative slope after that. Okay, so it's really a complicated mechanism that we are trying to parameterize. We can look at, you know, error estimates, and here, unlike the previous calculation, I really don't have the hundreds of realization. We ran the adaptive sampling. We really didn't know which of these 3 parameters was going to be most important, and we had to stop. And where we stopped here was after a mere 67 realization on sample. This is all there is. Okay, and the errors. Okay, and I'm looking at errors in temperature, and these are relative errors. Okay. And the important numbers are here. Obviously, they increase with time because I'm starting with an assimilated state and then letting it go. So at 915 they're small, at 918 they're large. Okay, and the relative errors get to roughly in the 10 to the minus 2, and they tend to concentrate right at where the center of the hurricane is, which is really not that surprising. And if you go down with depth, they tend to disappear, and in the sense that if you start with an assimilated state, the hurricane, 200 meters below the surface of the ocean, it's going to take a long time for the disturbance to feel the hurricane. Okay? So depth goes this way, this is time, and the deeper it is, we really don't feel the effect of the uncertainty in wind atmosphere. Comparison with observation is interesting. Okay? This is simulated data versus observed data. Okay? We're really in pretty good agreement. Again, the spread increases with time. This is September 15, this is September 17. But at least things are clustered around the main diagonal, in the sense that I do have hope to run an inference, or at least to start asking the question, what does the data teach me? Okay? If we didn't match the track of the hurricane and the intensity of the wind, the two things would not lie on the x-axis, and all of it would be systematic bias, right? Except possibly at depth, but at depth nothing happens. The important region here is what happens near the surface, or at least in the where the high winds are really coupling between the air and the water. So what we want to use right now is, can I use this setup to refine the priors on alpha, which is in the range I showed before, the uncertainty in the Vmax, which is the saturation speed, at which speed does the drag stop increasing and then you start shearing the waves, and after you reach that speed, does it stay flat or does it tend to drop? Can I refine the slope of what happens beyond this? Okay? And the interesting thing about this, typically the way these questions are addressed are through Bayes' theorem, okay, and running Markov chain Monte Carlo. Running Markov chain Monte Carlo on an ocean grid is impossible, okay, because the chain, even if it is small, will have thousands of points, right? Markov chain is a random process that would explore the posterior, okay? And what the nice thing that we are doing in here is that we are using our functional representation of the model as a surrogate for the model itself. So once we build the 67-member ensemble, we build the functional representation that is a good approximation, as I showed earlier, that is a good approximation of the model throughout. And we are feeding this to a Markov chain Monte Carlo, which is done extremely cheaply because there are no model evaluations anymore. Okay? So the surrogate, so here we are using a functional surrogate or a polynomial surrogate. There are other approaches that would use a Gaussian process surrogate. Okay? In this particular case, Gaussian process wouldn't have worked so much because there is quite a bit of activity towards the edge of one of the boundaries of the domain, as I will show in the next slide. So what I'm showing in here are the parameter Vmax, the parameter alpha, and the parameter m, which are uncertain, and we're assuming initially that the uncertainty is uniformly distributed in these type of intervals. Okay? And the curve in black is the posterior distribution. This is what the data is telling me. This is what the data is telling me, that the most likely distribution of the parameter is after the data is brought into in conjunction with the model prediction. So as far as where the curve is, remember the parameter alpha says where the curve is, how high is the parameter alpha shifts this curve up and down. Okay? The posterior is very sharp, which says that at least the data, we're really not in a position to do parameter calibration yet based on this data. Okay? But at least the vertical structure of the ocean, as measured by ITOP, is quite informative about where this curve is, and it really wants to concentrate it around the default or the optimized value that is used in the operational code, which is reassuring. Alpha equal 1 is what the operational code is. The Vmax value, okay, we have a map which is maximum a posteriori estimate, which is close to the edge of our domain, which is not nice. We get away with it because we have a very few, quite a few data points to the right of the map estimate. Okay? And it is really not as sharp, so we do have some uncertainty. Okay? With respect to what happens at the higher wind speeds, the data is completely uninformative. Okay? The prior is this, and the posterior is this. Okay? If I were to run a blind exercise, as you know, the ocean community or some of the people in the ocean community are constantly telling us, yes, there is a point that maximizes the likelihood. Yes, there is. But there is really no information gained in this curve. And you really want to look at entire distribution, whether there is quite a bit of information here, there is essentially no information there. There is always a maximum in the curve. If you want to maximize the likelihood, you feed the code and then spit out comes a number. This is the value that maximizes the likelihood. But does the data have any information here? The answer is no. And the reason that we are not able to refine this posterior is that at the XPT probe, we really don't have very high value of wind speed. Okay? So even though the wind speed, the high wind speeds do affect our model, it appears that the response, at least, and it makes sense, of the top surface of the ocean is really local to those higher wind speed, and the non-local effects are really not bringing in a whole lot of information, at least on a short duration event, that the 2-3 days that we were able to see.
So
yeah.
That's a sort of an identifiability, pseudo-identifiability issue.
Right. We wanted to learn, you know, is the data going to teach us something?
Right.
And I could have, you know, very easily concluded that no, the data doesn't teach us much, and then we move to the next problem. But it turns out that this data can be very valuable. And, you know, the value that we are extracting out of the exercise is informing the ITOP program that, you know, next time be a bit more foolish and fly into the ultra-high wind speeds and send a few AXBTs there, because we really need the data at the high wind speed if we are able to say that, yes, there is saturation, there is drop between saturation, or actually some models are even more elaborate than this. It goes non-linear between the highest saturation. But the first thing to look at is sensitivity. If we don't look at sensitivity, there is really no point in doing optimization, and there is really no point in doing inference. We are able to reduce the parameters that we are able to say something about. I could have really enlarged the exercise and included the background diffusion. It doesn't show. And whatever I infer, yes, I'm able to find a maximum, but there is really no information there, because the entire range doesn't induce any variability in the observable that I have or in the data that I measure. And then we want to look at, you know, what the posteriors look like, and then if things look sharp enough, then we want to go to the next step, which is trying to get an idea of model error. If I went to a different experiment, would it localize here, or what would the effect of resolution be, and so on and so on. So, in summary, sparse sampling is nice, it is neat, it is cool. It lets us get away with a much smaller number of realization that we would have otherwise needed. It really doesn't kill the curse of dimensionality, but in moderate dimensional problems, 3, 4, 5, 10, even up to 20 dimensions, it does make a big difference. Our ability to manage, treat, exploit massive scale data is really key. Before we are able to get, you know, sufficient confidence to turn, you know, sampling algorithms drive themselves on running pulling them by themselves adaptively, the kind of calculations that take weeks, months on a supercomputer, or thousands of processor hours running in parallel, we really want to, or would like to, if we can afford to, test their performance. And being able to test them on massive databases is something that is quite useful. We need to be able to carefully set up the forward problem. One of the lousiest thing that we can do is, we just take the problem, we start sampling, and we run statistics on the entire solution, and then we very quickly don't get much. So defining the right quantities of interest is essential. Getting a sense of sensitivities is essential. Reducing parameters that are not important is also very helpful. And the machinery of being able to come up with functional representation, whether we do them like we did over here with orthogonal bases, with polynomial chaos, whether we do them with Gaussian processes, but the machinery of being able, or the ability to represent the output of massive scale sampling in a functional representation is key, because it really opens the machinery of optimization, of inference, and design, and ultimately uncertainty management, and the design of experiments and observation to reduce uncertainties in parameters or data. Thank you much.
So in weather models, they've done a really good job with things like 3D var, 4D var, if they've got the adjoints for data assimilation. Yes. Is there an analogy in the ocean models? What's the status of these big data assimilation routines?
3D var and 4D var are being used.
Okay.
The difficulty with the ocean models is you really don't get a whole lot of 3D observations.
Yeah.
Whereas, so the tools are radars. We do have few buoys that are floating around. XPT is a new technology, but we really can't afford to fly airplanes, and we really can't afford to really man stations and have them floating and collecting data through the entire ocean.
Right.
So we are dependent on satellite data, and we are dependent on aircraft data, and these by and large give us surface fields, which is one of the big differences between the ocean and the atmosphere.
And I understand the Gulf is somewhat unique in the number of sensors, isn't it? Is that part of what makes it a nice place to study?
The Gulf has nice structure. I mean, it has features that are always recurring. If I'm able to show you at least go back to the map and just point to a few things that are here. Yep. So it is relatively closed. What comes out of here is a loop current that comes this way. There is flow out of this region between the tip of Cuba and Miami, and the dominant feature is the so-called loop current, which may be either in an attached state or a detached state. So anytime you look at the Gulf of Mexico, there is a loop current, and it may shed one or two large-scale vortices, and this is by and large the large-scale structure of the. We do have quite a bit of data on these inflows and outflows. So being able, you really don't need to assimilate a whole lot of. You have decent boundary conditions, and after a while, if you drive those, then you very quickly, even starting from a state of rest, in a few hundred years, you're able to get a state that is on a coarse mesh, and then you can use that as prediction for the next assimilation. So it is a nice. The bathymetry is known. Believe it or not, we don't know the depths of the ocean everywhere with millimeter precision. So the Gulf ends up to be a unique for A, it's contained, we do have decent inflow conditions and outflow conditions, we do have observations, and the dynamics have nice large-scale features that are recurrent.
So what's the scale of the mesoscale eddy simulation?
The ones that shed from the loop current are on the order of hundreds of kilometers, or tens of kilometers to a few hundred kilometers. Alina. Sorry.
So you mentioned that in your coupled ocean atmospheric model, wind is something which is deterministic, right? It's kind of counterintuitive, I would say, because wind changes very rapidly. So why it's deterministic as opposite to the ocean?
All the calculations that I showed today are not coupled calculations.
Oh.
So the wind is coming from WRF, which is run independently, and then we use the winds to feed HICOM. So the forcing condition is one forcing condition. We have just learned, you know, how to do things systematically in a coupled ocean atmosphere model. And we just got the courage, or you want to call it insanity or hallucination, to look at the other three coupling parameters. Obviously, the atmosphere is not just coupled to the ocean via momentum exchange, but also with mass and energy. And those have also different parameterizations and also different sources of uncertainty because they come from different experiments and so on and so forth. So the next exercise is going to look at additional uncertainties and additional coupling in a fully coupled model. But all the calculations I showed today, the winds were given, and the only thing that was changing was the coupling parameter.
Yeah, that was the same question actually, so it seems just counterintuitive.
It does, but
Yeah,
because
but
they are closely
I
coupled.
understand you thought that for the effect from the atmosphere on the ocean,
Yes.
so the high wind speed regimes are actually not so important.
Unless they're sustained. Yeah.
Yeah, but probably because of the size of the, but probably the other way it will be different. Because
we really can't tell until we sample all exchanges, because with mass transfer and with energy and with latent heats, it might depend on which temperature regime we are, and all the other phenomena that I really cannot look into my crystal ball and say with certainty this is what's going to happen. So on the fully coupled, I hope to come back in not too many years and tell you some more about it.
So yeah, I think time's is up.
One more question.
Sorry.
Yeah.
Typically, this drag coefficient is a function of Reynolds number. So I was just curious about that. You examine the drag coefficient as function of just velocity rather than finding some way of characterize some kind of form of Reynolds number, such as based on the boundary layer thickness or something. So is that going to change our way of understanding of this sensitive dependence or the feedback? Or?
For scales as large as just to get you to calibrate, the smallest grid size that I have is 1 kilometer. Okay, so this is the grid. Okay, the boundary layer is huge, and as far as any Reynolds number that we can dream of, they're essentially infinite Reynolds number. They're into the 10 to the 6s, 7s, 8s, 9s, even for wind speed of ½ meter per second. The drag law that you see is essentially a manifestation of the impact of waves. It's really a grip, and it's really a grip, even though many of the people in the community don't like that word. But it is effect of the wave component on the drag. Okay, all of this variation. It is really not a small scale turbulence. It's really the appearance of waves as wind speed becomes
Then
higher.
in that case, actually, it's consistent from this, the typical fluid mechanical observation that when the Reynolds number is very, very large,
Right.
then the drag coefficient will be primarily depends on the roughness.
Yes.
So in this case, your wave is actually serves as surface roughness.
Yes, except
Yeah.
that it chops off.
Yeah, but I was,
Yes.
I was just curious that you plot this x-axis as a function of velocity.
Because it is really a rho v squared to a rho gh, right? And the rho's are not the same. So it is a wind speed multiplying by a wind density squared, which is a pressure, and then you need to compare it to rho water gh in order to make a wave height out of that. And this is what gives you a roughness. So it is actually speed. We can probably reduce it so we can come up with a dimensionless number out of it, but this is really an artifact of how it is typically presented. But what it basically says is that until you hit somewhere in the 20 to 40 meters a second, you won't start shearing the top of the waves, which is you know, a motivation for showing the actual velocities because this is yet another mechanism. Initially, it's really a growth, and you want to represent it maybe in a reduced fashion, but then it is really shearing off the waves and forming sprays, which really causes that saturation. And this is another phenomenon which goes against doing it in a reduced or a Reynolds number type correlation.